Right, good morning. In this video, we are going to look at question 5 of the November 2015 question paper 1, which is a functions question with some inverse questions as well. Right, and actually question 5.6 contains a bit of calculus, which at this stage in the curriculum you have not done yet, but I will give you the answers to those as well. It will become clearer once we get to the differential calculus chapter. Okay, so question 5 is a straight line 2x minus 3. But it's limited between where x is negative 2 and 4, meaning this is a straight line that 2x minus 3 is a straight line that just continues, but they've actually made it so that it's cut off there. So we're only looking at a part of this graph by limiting the domain of the graph. And they say that the x-intercept of h is q. So this q is the x-intercept, and the first question that they ask is determine the coordinates of q, which is, as they said, the x-intercept of the graph. X-intercept I get by making y 0. So since the equation is y is equal to 2x minus 3, then by making y 0, let me just take the 2x that side and solving this. It's a fairly easy equation to solve. Then I get the x is 3 over 2, and obviously then the q coordinates which they ask is going to be 3 over 2, and the y value at that stage, since it's an intercept, is 0. So there's the coordinates of q. 3 over 2, 1.5, 1.5, all fine. Doesn't matter in what format you give that. Right, question 5.2 says write down the domain of the inverse function. Right, now inverse functions, by definition, the inverse function I obtain by swapping the x and y values, by replacing x with y and y with x. So since these two are exactly switched, also the domain and the range will switch. So the domain of the inverse is actually the same as the range of the function. So if I look at this function, the domain of this function was between minus 2 and 4, from there to there, on the x-axis. On the y-axis, you can see from there to there, meaning I actually need to get the y values there at the endpoints, and that will be the range of the function. So I need to get the y value where x is negative 2 and where x is 4 for this function. So in my function hx, which is 2x minus 3, I need to get h in the point negative 2, which is the starting point of the graph. If you substitute negative 2 in there, 2x, so I'm making x now negative 2 minus 3 is going to be negative 7. And I also need to get the y value where the x is going to be 4 for this function. So replace that x with a 4. It's 5. Alright, so the range of this function, the straight up function, has a range of y values that lies between negative 7 and 5. Right, so since that at negative 2 there, that's going, I worked out by substituting the negative 2, that's going to be negative 5, and by substituting the 4, the maximum value there, I get that y value 5. So you can see this graph on the y-axis lies between between negative 7 and 5, right? Which means then if this is the range for the function, negative 7 to 5 is going to be the domain of the inverse function. So that means that the inverse function, inverse h minus 1x, will have a domain of x that lies between minus 7 and 5. Right, the range of the function is the domain of the inverse function. Right, 5.3, sketch the graph of the inverse in your answer book, clearly indicating the y-intercept and the endpoints. Right, so since functions and inverse functions, the x and the y are swapped on a graph. This means that the graph of a function and its inverse is always a reflection in this 45 degree line y is equal to x. So I can just do it visually on the graph. Since my function is now going there, I'm just going to lightly draw it there. My function goes there. It's given there that it cuts the x-axis, the y-axis at -3, and I calculated it cuts the x-axis there at 3/2. If I just think of reflecting this graph there, can you see this line reflecting there? It's going to look something like that. Can you see? That's h minus 1x, just by doing a reflection in this line of the sketch that I have there. And the y-intercept, which is at -3, is going to become my x-intercept, and the x-intercept 3/2 becomes my y-intercept. A function and its inverse, the y is the x is the y, it's a swap. So the x-intercept becomes the y-intercept becomes the x-intercept, and I already know this inverse function should be limited to the domain between -7. So I'm going to put an endpoint there. Let me just extend the x-axis a little bit. I'm going to put an endpoint there at -7 and an endpoint there at 5. All right, limiting the graph to the domain as restricted by the function originally. Right, question 5.4 says, for which values of x will the function hx be equal to the inverse function x? Now I can do this algebraically, but I must first just calculate the equation of the inverse function. So to calculate the equation of an inverse function, if hx is given as 2x minus 3, this is now y. The inverse function I calculate by swapping the x and the y. So y becomes x and x becomes y, and then I must just make y the subject of the equation again. I can't leave it as x, I need to have y is equal to. So to do that, I'm going to take the 3 over to that side so that I have x plus 3 is 2y, and then divide by 2 throughout, making this half x, 3/2, and 1y. Divide by 2, divide by 2, divide by 2. So now I have y alone. I just actually want to write it as this. H minus 1x is of x plus 3/2. Right, so to get the inverse function, it's really straightforward, really simple. You swap the x and the y, and you make y the subject of the equation again. What they want to know in this question, though, is for which values will hx be equal to h minus 1x, for which x values. So I want to have hx equal to h minus 1x. hx is 2x minus 3 equal to h minus 1, which is a half x, plus 3/2. Right, now I don't like working with fractions, so I'm just going to multiply with the denominator 2 throughout. So this is going to multiply by 2, make it 4x, 6, 1x, and 3. I multiplied every single thing with 2, and now I want to solve for x. So 4x minus x is 3x, 3 plus 6 is 9, so x is 9 divided by 3, which is 3. The x is 3, and that's my answer. Since I only asked for which values of x is this, I can stop here. They might also ask what is the coordinates. Then you still need to take this x and substitute it into, well, any one of the two equations to just get the y value to go with it. But they asked x only here, so I can stop there. Right, question 5.5, bit of a more challenging question. Says Pxy is the point on the graph of h that is closest to the origin. Calculate the distance OP. So they want me to calculate this distance OP, where P is a point on this line such that it is the closest point to the origin. Meaning, if I take this as a distance, I'm going to use x, y as my points of P and 0, 0 as the origin, and calculate with the distance formula the distance of OP. So the distance of OP, where P is the point x, y, and O is the point 0, 0, is going to be x minus 0 squared plus y minus 0 squared, which is basically just root of x squared plus y squared. All right? So this is the distance of OP, and I want this here to be a minimum, because I want OP to be the shortest distance, the closest to the origin. So the shortest possible distance that I can get OP to be. I mean, there's also a point P on the graph, but that's a longer line than this one. There's also a point on the graph that I can make P, but that line is definitely longer than this one. So I want OP to be the shortest possible distance. So this I want to be a minimum. Okay, now since the P also lies on the straight line, I can maybe use a bit of simultaneous equations. I have the straight line y is 2x minus 3, so I can replace that y. Then I have OP is x squared plus 2x minus 3 squared. So replace that y with the y from the straight line, and then if I simplify this a little bit, I get x squared plus 4x squared minus 12x plus 9. What I did there is I just in my brain repeated this bracket twice and then multiplied it out. If you need to write it out and double check, that's fine. And then I have 5x squared minus 12x plus 9, like that. Okay. Right, so now for this under the square root, that part there is a parabola, right? And for a parabola to be a minimum or a maximum, I need to look at the turning point. If the parabola is this side, I'm going to have a minimum. If the parabola looks like that, I will have a maximum. And hopefully you can see that this is a parabola with a minimum because the a value is positive, then I have a smiley face. If the a value is negative, then I have a sad face. Right, so to get that coordinate, the x value there at the turning point, which is the one I need here, the turning point PQ, you can do one of two things. You can either take this part under the square root and do completing of the square to get the P and the Q both. Or there's an easy way to get that P by taking minus B over 2A. And since the B here is negative 12 and the A is 5, this gives me 6 over 5. So then I have the x value, 6 over 5, the x value at the minimum of this graph. And if I substitute it into this, I will get the length of OP at the minimum, where x is 6 over 5. So I'm going to do that. OP is root of 5x, which is now 6 over 5 squared, minus 12, 6 over 5 plus 9. And well, you can just type that into your calculator. I'm actually just gonna 5 times 6 over 5 squared minus 12, 6 over 5 plus 9. And that gives me 3 root 5 over 5 or 1.34. Right, so that gives me the length of OP. When it's at its shortest, it's going to be 1.34 units. That's question 5.5. Question 5.6, last question in this question, and we're going to end the video there. I'm just going to mention again, this is from calculus, which most of you haven't done at this stage. But for those of you who have started looking at calculus, this is a very good question. So I'm just going to quickly discuss that. Don't stress about it if you haven't started with the calculus yet. Okay, so 5.6 says given that hx is the derivative of f. So this graph here basically is the derivative of another graph where f is a function defined only for x between -2 and 4. So function that has the same restriction on the domain as this graph here. Then it says, explain why f has a local minimum. Okay, right. Now, if you've started with calculus, hopefully you know this then already. This is super important in calculus. In calculus, the derivative of a function is the gradient of the tangent. Okay. The derivative is the gradient of the tangent, right? So explain why f has a local minimum. If they say that this function is the derivative, this function is the gradient of the tangent to the graph that I'm looking at f now. Meaning if I look at this as the gradient here in this section, the gradient is negative, right? Meaning the graph is going down, the actual graph. This is just the gradient. The gradient is negative, then the gradient is 0, and at a 0 point I have a turning point, and then the gradient is positive. So the gradient is negative, 0, turning point, and then positive, meaning it makes a smiley face parabola. You see this section, negative gradient, so the graph is going down. Then it is a 0 gradient, meaning the graph is stationary, and then it has a positive gradient, meaning the graph is going up. So you see this is a parabola. So you can say something in the likes of gradient f accent x is negative, 0, positive. That is positive a parabola. All right, the gradient is negative, 0, positive. Right. So you can say something like that. Explain why f has a local minimum. Write down the value of, or you can say something like the 0 point is the turning point of the graph. The 0 point of the gradient is the turning point, and since before the turning point the gradient is negative, and after the turning point the gradient is positive, that means the graph went down, stationary up. So you can say something like that. Okay, then 5.6.2 says write down the value of the maximum gradient of the tangent. I said the gradient of the tangent is the derivative. Now, since the derivative is this function, the maximum gradient of the tangent is the function. So the maximum of the function to the graph of f. So the maximum of this function is going to be 5. 5.6.2 maximum equals 5. Okay, that's the maximum gradient. If they asked the maximum point, you actually need to go substitute the x value 4 into the function, but I don't have the function, I just have the gradient. This is my gradient. The maximum gradient is going to be 5. Okay, that's question 5.